The program introduces sample moments and their importance in statistical estimation and financial risk management. Because analysts rarely have access to an entire population of financial data, they rely on samples to estimate population characteristics. The topic explains that sample statistics such as the sample mean, variance, and standard deviation serve as estimators of the corresponding population parameters. These estimators allow risk managers to infer expected returns, market volatility, and risk exposure from historical observations. Accurate estimation is critical in finance because investment decisions, portfolio optimization, and risk models depend heavily on reliable statistical summaries derived from limited and often imperfect market data. The sample mean is presented as the primary measure of central tendency and represents the average value of observations within a dataset. The program explains that the sample mean is calculated by summing all observations and dividing by the sample size. In financial applications, the sample mean is commonly used to estimate expected asset returns, average interest rates, and long-term performance measures. The topic emphasizes that while the sample mean is an unbiased estimator of the population mean, its reliability depends on the size and representativeness of the sample. Larger samples generally produce more stable estimates, reducing estimation error and improving confidence in the conclusions drawn from quantitative financial analysis. Variance and standard deviation are then introduced as measures of dispersion that quantify the variability of observations around the mean. Variance measures the average squared deviation from the mean, while standard deviation represents the square root of variance and is expressed in the same units as the original data. These measures are fundamental in finance because volatility is widely interpreted as a measure of investment risk. The program explains that sample variance requires a degrees of freedom adjustment, dividing by n-1 rather than n, to produce an unbiased estimator of population variance. This correction is especially important when analyzing small datasets commonly encountered in financial research and risk modeling. Topic expands the analysis beyond the first two moments by examining skewness and kurtosis, which provide deeper insight into the shape of probability distributions. Skewness measures the asymmetry of a distribution, indicating whether outcomes tend to cluster toward one side of the mean. Positive skewness reflects a longer right tail, while negative skewness indicates a longer left tail. Kurtosis measures the heaviness of distribution tails relative to a normal distribution. High kurtosis suggests a greater likelihood of extreme outcomes, which is particularly relevant in financial markets where rare but severe events can significantly affect portfolio performance and institutional stability. The program emphasizes that estimating higher moments accurately is essential because financial return distributions are often non-normal. Traditional models that assume normality may underestimate the probability of extreme losses if skewness and kurtosis are ignored. Risk managers therefore rely on these additional moments to evaluate tail risk, stress scenarios, and the likelihood of abnormal market events. The topic also explains that higher moment estimators are generally more sensitive to sample size and outliers than estimates of the mean or variance. As a result, analysts must carefully interpret skewness and kurtosis estimates, particularly when working with volatile financial data or limited historical observations. Overall, topics provide a statistical foundation for quantitative finance by demonstrating how sample data can be used to estimate the characteristics of broader populations. The program highlights the practical importance of estimating central tendency, dispersion, asymmetry, and tail behavior when constructing financial models and evaluating risk exposures. These estimation techniques support a wide range of applications, including portfolio optimization, derivatives pricing, risk forecasting, and regulatory stress testing. By understanding the strengths and limitations of statistical estimators, candidates develop the analytical skills necessary to interpret financial data accurately and make informed decisions under uncertainty in increasingly complex and dynamic financial markets.